Okay, so this is I'm going to go over all the questions that I gave you for for the worksheets, and I'm not going to be able to draw everything, but you'll see it on the PowerPoint. I mean, on the presentations. um, I'll refer to you to what you need to know as far as drawings and uh, other things. Okay, the three components of test three are going to be carboxyl group, which include esters and carboxylic acids, polarity, and then lipids. All right. So the first thing we covered was the very first thing we covered, and it's I think it's videos, the last videos, 8, 9, carboxylic acids and esters. So you'll have to be able to draw a functional group associated with these two molecules. So there's the carboxyl, which is the CO and O, and then and then the carboxylic acid has the H at the end, so COOH, and the ester has the COO with carbons on either sides of the on one side of the oxygen, yeah, on side of the hydrogen. So just look at the notes for that. So what is a carboxylic acid and ester? I just told you. So draw the following structures, and they'll be in the next slide. And so will the oxidation of ethanol to acetic acid to acetic acid. And number 5 as well, and number 6, and number 7 is called hydrolysis of an ester. So, and let's go over those drawings now. So over here, let me get my little pointer thing. Okay, up here it's pentanoic, has 2,3. That should be 2,3-dimethyl pentanoic acid. So you can see it's 1, 2, 3, 4, 5. That's a methyl and a methyl, and this is a carboxylic acid. All right, formic acid is 1 carbon. Carboxylic acid and acetic acid is a 2 carbon. The rest of the carboxylic acids end in oic acid. This would be formerly methanoic, and this would be ethanoic, but that should be on the table. Okay, so this is the oxidation of a primary alcohol to aldehyde, which we talked about last test, specifically ethanol to acetaldehyde, and then finally you can take an aldehyde and add oxygen to it to form a carboxylic acid. And it does, so this could be like propanol, which has another carbon here, and it would turn into the associated aldehyde here, and then into the associated propanoic acid here. So the key thing is that it's a primary alcohol. It only has 1 carbon attached to the hydroxyl, and that can be oxidized to aldehyde and so forth, acetaldehyde. Okay, in the formation of an ester, okay, you take an alcohol and a carboxylic acid, you snap off the hydroxyl and the H, combine the two, and you get an ester. Okay, an ester is, if you notice, it has the carboxyl group, but instead of having an H over here, it has carbon. So this guy would be propylbutane. So you take the 3 carbon, which is a propyl, and the oic acid turns into an 8. So that's your ester. And this is the ester bond. Okay, what is polarity? Well, I gave you a definition. I believe it's that it's how electrons are distributed, or how they share it on a molecule. And there's 2 different types. There's polar molecules where the sharing of electrons is unequal, or one side of the molecule is more negative than the other. And then you have a nonpolar molecule where the shared electrons are equally shared on the molecule, and it doesn't have any polarity. Okay, and I went over the 2 things that determine polarity, and that was the electronegativity of the atoms attached, and also the shape. And then I gave you 2 ways to identify if a molecule is polar or nonpolar. One way is to look at the structure, like down here, And if it has different things attached to it, like this case, it's polar, and if it has the same things attached, then it's nonpolar. All right. So a thing can include an atom or a lone pair. Okay. So it looks like it has the same things attached to H, but it really doesn't. The center atom has a lone pair attached as well as H, so it makes it, so that's a way to identify if it's polar. It's not because. Another way I told you is if you look at the chemical formulas, like in these two cases, and if the ratio of carbons to oxygens is greater than 3 to 1, then it's probably going to be nonpolar. So in this case, the ratio is 2 to 1, so this is going to be a polar molecule. And the ratio here is there's 12 to 2 or 6 to 1, so this is greater than 3 to 1, so this is probably going to be a nonpolar molecule. Okay, molecular interactions. Okay, molecular interactions are interactions between molecules. And why do they have, the interactions are attractions, not repulsions. Okay, what are differences in the interaction between solids, liquids, and gases? Solids have lots of interactions between the molecules. And remember, interactions are not bonds, they're just attractions. Okay, so when we're going to be talking about melting, you take a solid and you change it to a liquid, and what happens is the particles separate from each other. So when they're solids, they're all connected to each other through interactions, and when you heat it up, you break some of those interactions. And for a gas, there's no interactions at all between the particles. Okay, what type of interaction do polar molecules? Dipole. Okay, and to explain the interaction, well, I'll show you a diagram of that. You have the plus side of the molecule is interact with the negative part of the other molecules, and that interaction is called an electrostatic attraction between polar molecules. And an electrostatic attraction between polar molecules is known as a dipole-dipole. So all polar molecules interact with each other, and they do it quite easily. Just line up, we put them in there, and they just naturally attract. Okay, a typical type of polar molecule is water. Water is a polar molecule. And so all polar molecules can interact with each other. So if you take any polar molecule, it's going to interact with water because water is polar. So what we say, because of that, is all polar molecules are hydrophilic. Hydro means water, philic means love. So another name for polar molecules is hydrophilic. Okay, nonpolar molecules do not interact all that well. But they can. They just have to know how. They got to learn how to like each other. They can like each other. And when they do interact, the interaction is called London dispersion forces, and I will shorten that to LDFs. Okay, so explain their interactions. So the interactions are really, really, really weak electrostatic attractions. And what you really want to do is you want to see if you can increase those interactions. And the way you can do that is by get these molecules really close together. You can get them closer by pushing them together, add pressure. You can get them closer together by adding, if you add more particles into an area, you're going to have them crashing into each other. You can slow them down by decreasing the temperature. You can make them bigger, increase their surface area, so they can't avoid each other. So any way you can make them run into each other more often, you're going to increase London dispersion forces. Okay, what happens when you put oil and water? Okay, so the way that I described it is you take, when you put oil and water, well, the oil is going to come crashing into the water, and the water is going to go, and the water's going to try to find other waters to interact with because they like other water molecules. It's not that they don't like oil molecules. And when that happens, it forces the oil molecules together. Just like we said up here, it forces when you force nonpolar molecules together, they end up liking each other. So when water forces the oil together, because it's trying to get to itself, it actually it lets the oil molecules like each other better. And they stick together a lot better. Okay, typically how is this interaction between oil and water, or nonpolar and polar? So oil is nonpolar, water is polar. It's typically described as water not liking oil, or oil not liking water. That's not what it is. So it's talked about as water not liking oil, oil not liking water, and because of that, this type of interaction is often called hydrophobic. So nonpolar molecules, because they don't look like they interact with water, are called hydrophobic, which means water hating or fearing. Okay, now we can get into lipids. What defines a lipid? Just nonpolar biological molecules. The key thing is nonpolar. What two types of lipids are there? Well, there's fatty acids and there's steroids. And the reason why they are both nonpolar, that's because they're both nonpolar. They don't dissolve in water all that well. It's because they have lots of carbons. Okay, what are two parts of fatty acids? Well, one part is the carboxyl, the COOH. And then the other part is the long carbon chain. It's typically between 10 and 18, 20 carbons. What are the four types of bigger molecules that fatty acids make? Well, one is a wax, right? Another one is the triglyceride, then soaps, and then phospholipids. Okay, so there are different kinds of fatty acids, saturated and unsaturated. Saturated have all single bonds behind in their carbons. Unsaturated have at least one double bond. Where do we cover saturated and unsaturated before? We covered that when we talked about alkanes and alkenes. Alkanes were called saturated hydrocarbons because they had all single bonds. Alkenes were called unsaturated hydrocarbons because they had at least one double bond. All right, so we talked about this in the last slide. What happens when things melt? So like if you have ice, when ice melts, what happens is the water molecules, when it's a solid, all the water molecules are interacting with each other. But when you heat it up, what happens is that's a dipole-dipole interaction. And when you heat it up, what happens is that there's energy given to the molecules and they start to separate. And that breaks the interactions between the water molecules. It doesn't break the water up. I mean, the individual particles into hydrogen, oxygen, it just breaks the attraction between them. Okay, now in terms of how does that relate to what we're talking about? Well, so in the diagram, it showed you fatty acids that have lots of carbons and will have high melting points. And why is that? Well, long fatty acids can have a lot of interactions because of their tails wrapping up around each other, tangling up. And that tangling increases the London dispersion forces. The double bond, if you add a double bond, what it does is it stiffens up the chain, and so they can't wrap around each other anymore. And that's why they, if they're same length, saturated, unsaturated will have a lower melting point because the double bond doesn't allow as much a tangling effect. Okay, and okay, so that talks about the general properties of fatty acids, and now where do they go into the four types? The first type was what is a wax? And a wax is an ester made out of a long alcohol and a fatty acid. And so they have lots and lots of carbons in them. That means it makes them really hydrophobic, and they repel water really well because they are very hydrophobic. Okay, triglycerides. Uh, what is a triglyceride made out of? A triglyceride is made out of a glycerol and three fatty acids. All right, so make sure you know how to draw the formation of triglycerides just like I did on the board. Okay, so I'm not going to redo that here, but I drew it on the board where you have the glycerol and then plus the three fatty acids. And then I had an arrow, and then what you do, and then it forms a triglyceride plus three waters. Okay, so what are the two types of triglycerides? Well, there's fats and there's oils. And the difference is that fats are usually found solid at room temperature, and oils are liquids at room temperature. Fats are found usually in animals, and the oils are found in vegetables. Why do fats have higher melting points? It's because the fatty acids found in the triglycerides tend to be mostly saturated. What is the name of the reaction that turns triglyceride back into fatty acids and glycerol? Okay, so the formation of a triglyceride is the formation of an ester. So you're forming an ester, you're taking a glycerol, which is alcohol, and the three fatty acids, which are carboxylic acid, and forming an ester, which triglyceride is, and water. Then you can reverse the reaction, take the triglyceride and water, and turn it back into fatty acids and glycerol, and that's called hydrolysis. Okay, what are the three functions of triglycerides in our body? One, triglycerides can carry fatty acids to cells. So it carries three at a time, which is efficient. Instead of just having one float around in the blood going to the cell, you can have this guy taxi. So a triglyceride is like a taxi. It taxis the fatty acids to your cells to be used for energy, possibly. So that they could be moved to your cells for energy. That's one function. Another function is to move the fatty acids to adipose tissue for storage of energy. And then finally, the function is you can move the fatty acids from the adipose tissue to your cells for energy. All right. What is hydrogenation? Hydrogenation is where you take a unsaturated hydrocarbon, either an alkene or a unsaturated fat, and you add hydrogen through it through a chemical reaction. So and when you do that, it removes the double bond and makes it saturated. So we saw this before when we talked about alkenes to alkanes. We took alkenes, added hydrogens, and formed alkanes. Okay. And hydrogenation is used in industry to convert oils, vegetable oils, to solid vegetable oil. In a sense, making vegetable oils kind of like fats, and they can be substitute fats for making food, like shortening. Okay, what are soaps? Well, a soap molecule is basically what are two parts of soap molecule. So a soap molecule is a fatty acid that's had the carboxylene, the COOH, changed. And what has happened is the H has been removed and a negative charge has been put on it. And when it does that, it makes the soap molecule, it makes a fatty acid molecule charged on one end, polar, and non-polar on the other end. So what we say is the head is polar, the COO, and the tail is non-polar. Why does the head of the soap molecule interact with water? Because they're both polar. Why does the tail not interact with water? Well, because it's non-polar. Explain how soap forms a micellar water, and it went over that. Okay, so the tails get pushed into the middle by water, and they interact through London dispersion forces, and the heads interact with the with water. And then part 4, I went over that and the diagram on the board. And you just make sure you know how to do that. So basically what it is that when you add, you have to add water to hand first, and then you add the soap, and the soap, that the water forces the soap molecules orientate themselves and so forth. And right, that's, you just check the notes for that. All right, next thing is phospholipids. What is the similarities between a phospholipid and a fatty acid? Okay, they both have a glycerol. They both have, they both look like triglycerides. The difference is the phospholipid replaces one of the fatty acids with a phosphate group. And when it does that, it makes it like a soap molecule, where the phosphate part actually becomes like a head on a soap molecule. And so a phospholipid looks like a soap molecule, but instead of just having one tail, it has two tails. What kind of structure does it form? It forms a bilayer. Okay, where the tails, the tails line up. The ends of the tails interact through London dispersion forces, and the sides of the tails interact with side to side through London dispersion forces, and the heads interact with the water through dipole-dipole. So there's 3 interactions here holding together a phospholipid bilayer. There's the internal London dispersion forces, and there's 2 types. There's the tails interacting tail to tail, end to end, and then they also interact side to side. And then on the outside, the heads interact with polar heads interact with water. Okay, so here's part 4. Draw a phospholipid, describe what holds together. Basically, I just told you that. Where are they found? They're found in cells. Okay, it's what a cell membrane is. Why do cells have membranes? It's keep the outside of the inside of the cell from the outside of the cell. What is the fluid mosaic model? Okay, so I told you that that a cell membrane is more than just phospholipid bilayers. It has steroids and so forth, and that's what you have to define. So there's steroids that hold them together. There's cell receptors. There's there's carbohydrates. There's that cell recognition and so forth. And I think and then what are 3 different ways things get out of cells? One is called diffusion, which is where small nonpolar molecules can move in and out, like oxygen and carbon dioxide. There's facilitated transport, where there's these proteins which act like channels that allow bigger molecules to go in and out of the cell. And then there's something called active transport, which are kind of like facilitated, but now you actually have, instead of just allowing things to pass through just whenever they want to. They have to pay a toll, and that's they have to ATP has to be released or given for these to move through. Okay, steroids. So this is the second type of lipid. The first type of lipid were fatty acids and their constituent things. Similarities between steroids and fatty acids is they both have lots of carbons. What is the main structure of steroids? Well, they have the 3 ring structures. What are some of the roles of cholesterol? Well, they're listed. The cholesterol is the most important steroid in our bodies. Sex hormones and the other steroid hormones are made from cholesterol, vitamin D, I believe, and okay. As far as sex hormones and adrenal corticals, what do you need to know? Just need to know the names. Like there's testosterone and what are the roles, and I went over them in the slides. And you won't have to draw them. You just have to know their names and some of their and their functions that I told you. You cover these more in depth in A&P, I believe. All right, and finally, lipid transports. Okay, what are lipid proteins? Lipoproteins carry lipids through the blood. Why do you need to do that? Well, if you didn't have lipoproteins, the lipids would try, if they got into your blood, they would basically just clog up your blood because water and oil don't mix, and that you die. All right, and so what you have to do is you have to have a way of transporting the lipids without the blood noticing it, and so that's what lipoproteins do. They transport the lipids. There's 3 basic types. One type is the chylomicrons and VLDLs, and they take lipids to the cells for whenever the cells need energy or to store lipids as energy. LDLs move things like cholesterol to cells so that cholesterol can be made into steroids and so forth. And HDLs are lipoproteins that go around to look for any kinds of lipids that are just straggling around in the blood that need to be picked up. Okay, kind of like a garbage truck. How are lipoproteins similar to how micelle structure of soap work? Okay, in the micelle structure of soap, what it does is it hides the oils or grease or from the water. Well, lipoproteins do the same thing. What they do is they have a polar outside and a non-polar inside, and the lipids go inside the lipoprotein, hang out in there with their non-polar interactions, and then the water doesn't see them because they're hidden. I went over how LDLs and HDLs are used for blood work. Okay, way of measuring cholesterol. And why is it incorrect to call LDL bad cholesterol? First of all, LDL is not cholesterol. It's a transporter of cholesterol. It's not bad because it has a job, and the job is up here. Okay, it's just used as a way of diagnosis of too much cholesterol in your blood. Okay, and that does your review. Okay, all right. Use this with the the presentations for the test, and I'll tell you how we're going to do the test in a day or two. All right, bye.